So did anyone do anything interesting this week? You had hot pot. Do they still only allow outdoor dining for places like that or no? Or did you have hot pot at home? Okay. Right, so all of you just ate food. I see. I see. You started cooking? Really? What did you learn how to cook? Meatloaf? That's cool. Yeah, my family is Chinese, so they cook Asian food. But then like every time I cook something, I look up recipes and like I cook like steak and stuff. So I cook like white people food, and my parents are always judging me. Yeah, I feel like that's true. Asians don't bake. In fact, the oven in my house doesn't even work, so can't even put anything in the oven. All right. How are you doing with the question? Is everyone done? But I don't even know why I ask these questions. Every time I ask a question, like only one person answers me. So I'm just gonna say everyone is done. Let's go over it. Let me switch screens. Okay, so why do you guys walk me through the steps? What do we do first?
Factor the denominator.
Okay, I can do that, I think. So if we factor the denominator,
I guess we could use difference of squares.
yeah. If we factor it, we will have x minus 2, x plus 2. All right, I factored it. What can I do now?
You could split the denominator and write it like integral a over x minus 2 plus b over x plus 2.
Okay, yeah. So we want to do the partial fraction decomposition thing. So we split into two different fractions. Okay, but we don't know what the denominators. Well, we don't know what the numerators are, so we'll just leave it as variables for now. And because the denominators are linear, then the numerator is just 1 degree less, so it's going to be a constant. So just a and b. Okay. There we go. Now what?
we need to like equal the numerators.
Mm-hmm. Give me 1 second. So when we equal the numerators, we have to, we come up with the following equation. So if we were to say add these two fractions that we just separated, we would have a times x plus 2 plus b times x minus 2. This numerator has to equal our original numerator, which was 1, right? So this is the equation that we will get if we equal the numerators. Okay, and then at this step, remember what our goal is? Our goal is to solve for a and b, right? So there's two ways we can do it. One way is just to choose very convenient values of x to get two equations. The other way is just to distribute everything and then solve it like the brute force way. So which way do you guys want to do it?
Using the roots is easier.
Yeah, we could. So what are the convenient values of x, or what are the roots? So
2 and -2.
yes. So let x equal 2. That will give you the following equation. That will give you 4a. The b part will go away because you'll get 2 minus 2, which is 0, is equal to 1. So this means a is equal to 1/4. Okay. All right. So we solved for one of the variables already. And then you guys said the other root was -2. So let x equals -2. That will give you -4b equals 1. So b is -1/4, right? All right. Okay, good. So now we can rewrite the original integral. So this would be integral of 1/4 over x minus 2 plus -1/4 over x plus 2 dx. Okay. Now the whole reason why we did this splitting of the fraction is because these two fractions by themselves are very easy to integrate. So what would the answer be? Can someone finish this?
It would equal -1/4 ln x plus 2, opposite value of x plus 2, plus 1/4 ln absolute value of x minus 2 plus c.
Yeah. Let me just write it the other way just because this term is first. So 1/4 ln absolute value of x minus 2 minus 1/4 ln absolute value of x plus 2 plus c. Okay, so that should be it. All right. Any questions on that before we move on?
Professor, can we go over an example like number 2 where like the denominator is not linear?
Yeah, we'll definitely have more examples like that later on. Yeah.
Okay, we will go over it tomorrow. Cool.
Yeah. Okay, so this is an example we just did. Let's see the next example. Okay, so this one looks a little bit scary. Let's see. So do you guys remember one of the conditions for being able to do partial fraction? If I scroll up, we said that the numerator and denominator are polynomials, but the degree of the numerator has to be less than the degree of the denominator. If that's not the case, we have to perform long division. Okay, so if we look at this example here, our next example, can you guys see how we have to perform long division? Right, so the degree in the numerator is 4, and then the degree in the denominator is 3. So it's not less, 4 is not less than 3, so we have to do long division here. Okay, now the real question is, how many of you remember how to do long division? Okay, so people that actually remember, gonna have to help me out here because it was a pretty involved process. Okay, so what we're gonna do is, first we're gonna set up the chart for long division. So go something like this. I draw this symbol. And then underneath the, what is this symbol even called? No idea. I'm gonna put the numerator inside of the symbol. So it's x to the 4th minus 5x to the 3rd. The dividend. I think the dividend is what you put inside of it, but the actual symbol, I don't know, it probably has a special name. Plus 6x squared. I do remember that from long division, you cannot skip any powers of x. So if you're missing any powers of x, you have to fill it in. So we're going from x squared to 18, so we just skipped one. So I have to fill it in now. So it's 0x minus 18. I believe that's how you write the dividend. And then for the divisor, that goes outside of the symbol. So it's x to the 3rd minus 3x squared. Okay, so that's how you set it up. Yeah, I believe in other countries, they taught you how to do it differently. Well, I mean, it's the same algorithm, but like you put the divisor and the dividend in a different place, but it's essentially the same process. It doesn't matter, as long as you have the same answer, I'm okay with it. So how this works is you take the leading term of the divisor and the dividend and you divide those things. So we're going to take x to the 3rd. And how many times did that go into x to the 4th? So that was how long division works. So we're basically doing x to the 4th and x to the 3rd. What does that give you? That gives you x, right? So that will be your first term in your quotient. So let me put that here. Then you're going to take what you have in your quotient and you're going to distribute it back to the divisor. So when I distribute x back to the divisor, I'm going to write it underneath the dividend. So that will be x to the fourth minus 3x cubed. Okay. And then if you recall from regular division, the next step was to just subtract. Don't forget your parentheses. So x to the fourth minus x to the fourth is nothing. That will always be the case. The first term should always cancel out like that. And then we have minus 5x cubed minus negative 3x cubed. So what's that? So we're trying to do a negative 5x cubed minus negative 3x cubed. So that's minus 5 plus 3, which is negative 2. So we have negative 2x cubed. Okay. And at this point, you're essentially you've completed one cycle of the division algorithm. So now everything just repeats itself. We're going to bring everything down. So this is 6x squared plus, just bring down that one. So we're going to go back to the first step, which is to take the leading term and then divide it by the leading term of the divisor. So we need to do negative 2x cubed divided by x cubed. And then what does that give you?
-2.
Yes. So that goes in our quotient. And then we're going to take the negative 2 and we're going to distribute it back to the divisor. So that should give you negative 2x cubed plus 6x squared. Okay. And then we subtract. So the first term should always cancel out. Then we have 6x squared minus 6x squared. Oh, okay, well that cancels out too then. So we just have 0. And then let's bring down all the remaining terms. So plus 0x minus 18. So this is the only thing left. Okay, now who remembers how to tell when you should actually stop dividing in this algorithm?
When we're out of, like, wear out the exponents or something.
Yeah, I mean, yeah, you're right, but like there's a more formal way of saying it. So let me see what other systems are saying. When the remaining stuff is a lower power. yeah, that's basically it. So when the remainder has a degree that's lower than the divisor, then you cannot go any further. When the remainder no longer contains x. It's not just x, because even if we had x here, we would still not be able to continue because we can't divide it into x cubed. So it's when in this question, it's when our remaining stuff has a lower power than 3. That's when we'll stop because the divisor has a power of 3. Okay. So because it's just 18, we have to stop here. This is our remainder. So our quotient is x minus 2 and our remainder is negative 18. So how can we use this information to do our example?
We can rewrite the integral in terms of the quotient and the remainder.
Yeah. So let's do that. This will be, instead of writing this giant thing, we can write it as x minus 2, which is our quotient, plus the remainder over our original denominator, 3x squared. And does anyone need clarification as to why we can write it like this? Okay, well, I'm going to tell you guys anyways. So the reason why we can write it like this is because if you have, say, like 7 divided by 2, that gives you 3 with a remainder of 1, right? So instead of writing 7 divided by 2, I can just write 3 plus the remainder over the original divisor. Okay, so that's basically what we're doing with polynomials. So that's the first step of this question done. Hopefully this is going to refresh you guys on how to do long division. Let's continue the integral process. No, just keep it up blue. So the x minus 2, that part we don't need to focus on because we know how to integrate that. So we can just ignore that for now. Why can't we do synthetic division? Yeah, so if you guys remember, there was another method of dividing polynomials called synthetic division. Does anyone remember why we're not allowed to do synthetic division here?
I think it's because it's x cubed. I think synthetic works for only like a small value when it's like less than. I'm not sure though.
Yeah, so synthetic division only works when your divisor is in the form x minus c. That's the only time you can do synthetic. So this is not in the form x minus c, so you can't do synthetic here. Okay, so we can focus on the negative 18 over x cubed minus 3x squared. How can we make that simpler? I can factor the denominator, right? So that will give me x squared, x minus 3 dx. Okay. And then what do you guys think we're going to do with this term now? Separate into 2 fractions. Yes, we're going to do partial fractions. So the question is, when we break this into many fractions, how many fractions are we going to have? So I'm going to split negative 18 x squared x minus 3. How many fractions will we have? Is it 2? Three. Yeah, so it turns out to be 3. And the reason is because of that chart I gave you guys earlier, which I'll paste just for reference. So you guys remember this chart? What this chart is saying is that if you have a linear function or a linear expression in the denominator with a power, then you need a specific fraction for every power. So we do need 3 fractions here. Let me just write it out first. So the x minus 3 is going to be 1 fraction. So that's here. The x squared, we're going to have to split x squared into 2 fractions. So 1 fraction is just going to be x. The other fraction is going to be x parentheses squared. Okay. So that's how you would set it up. And then the numerator will be all just constants, because everything in the denominator is linear. All right, is everyone okay up to this point? Okay. One thing to be careful of is I've seen some students write bx plus c for the second fraction because they think that the denominator here is actually like a quadratic because x squared. But it's you can't think of it as like a quadratic because you want to think of what's in the parentheses, which is just an x, which is linear. Okay, so do be careful on that. Why is it b over x squared? It's because if you look at the partial fraction table that I gave you guys earlier, specifically this situation here. So our denominator is x squared, which is a linear function, but raised to a power. And then when you have that situation, you need 1 fraction for every power. Okay, so this is the fraction for the first power. This is the fraction for the second power. So in parentheses, this is like your x, and then k is like your squared. Shouldn't c be over some x cubed since the powers are increasing? Yeah, but we don't have an x cubed because our original question only goes up to x squared. So we can just stop at x squared. Why doesn't it fit the third row? Let me see what the third row was. So this is the third row of the table. Yeah, I guess you could use the third row if you wanted to, but if you wanted to use the third row, then you would do ax plus b over x squared plus c over x minus 3. Yeah, this would also work actually. And any one of these methods would work. So it doesn't have to be this situation. So I guess just go with whichever one you feel comfortable with. I prefer the first way just because they're all just constants. But the second way, I guess, is also fine because you have just 2 fractions instead of 3. But yeah, these should all give you the same answer once you finish them both. Okay, let's try to find A, B, and C. So when we set the 2 numerators equal to each other, we will have negative 18 is equal to A, and then you multiply by whatever is missing. So it's missing an x. It's also missing an x minus 3 plus b. This one is just missing an x minus 3 plus c. And this one is just missing x squared. Okay, so for this one, again, there's 2 methods to solve for A, B, and C, but this situation, I would probably say using the roots is the easiest. So what are some convenient values of x we can pick?
Zero and 3.
Yeah, so when you have x equals 0, the first term goes away. So you're going to get negative 18 is equal to negative 3b. Then this term, the c term also goes away. So this means that b is 6. Okay, so we found one of the variables. What's another good value of x we can pick? 3, yeah. If we let x equals 3, then we will have negative 18 is equal to, the first term goes away, the second term goes away, and then the third term is just 9c. So this gives us c equals 2. Negative 2, yes. Where did the negative 18 come from? That was our original numerator. This is negative 18, which goes here. And then when we set the numerators equal to each other, the negative 18 was over there. Okay. Okay, so we found B and C. We just need to find A. But it seems like we're out of convenient x values to choose. So when that happens, you don't have to use the roots. You can, remember, this equation that we wrote holds for any value of x. So you can just choose an arbitrary value of x just to get another equation. So I don't know, what's easy? I guess we can just choose 1, right? So this will give you negative 18. So when x is 1, we will have negative 2a plus or minus 2b. Minus 2b plus c, right? So we have this equation when we let x equals 1. But remember that we already found b and c, right? So we can plug those into the last equation. So we have negative 18 is negative 2a minus 2 times 6 minus 2. So this is negative 18, it's negative 2a minus 12 minus 2. So that's minus 14. And then, so this is negative 4 equals negative 2a. So a is 2. I hope I didn't make a mistake there. Okay, so that's a, b, and c. Okay. All right, so let's write the integral. We have x minus 2, that was our quotient, plus a was 2, b was 6, and c was negative 2. Oops, I wrote a. All right. So now we should be able to integrate this without much issues. What's the integral of x? X squared over 2, yes? We're integrating, so we don't need the integral sign anymore. Delete. So x turns into x squared over 2, and then what about negative 2? That turns into negative 2x. Then 2 over x, what is that? Yep, very good. So that's 2 ln of x. 6 over x squared, how do you do that one? Okay, so recall that if we have 1 over x squared, you can rewrite that as x to the negative 2 power. And then when we integrate, we add 1 to the exponent and then divide by the new exponent. So 6 over x squared just turns into negative 6 times x to the negative 1. Actually, I can just write it like this. Negative 6 over x. Yeah. Now the last one, negative 2 over x minus 3. What's that? So that one's negative 2 ln. Okay, plus c. Okay, so that's that example. Now's the time to ask questions if you have any. Someone mentioned that they wanted to see an example where the denominator had like powers greater, that was like not linear. Was this example like good enough to, like, is this the kind of example you're looking for or no? I don't remember who asked that. All right, let's move on. Okay, so here's the next example. Now that we have more practice, this is what I want you guys to do. So I want you guys to set up the partial fraction and solve for your A, B, and C, or solve for your numerators, okay? And then just stop there. So we'll integrate it together at the very end. All right, I will give you guys 5 minutes. I think this question is from your homework, if I remember correctly. By the way, that formula on the bottom, that's one of the formulas that you'll need for the integrating step, not for the partial fractions. Okay, how's everyone doing? Do you all need more time? Sure, one more minute. All right, let's do this example. So we want to factor the denominator. I don't think there's much you can do here besides pull out an x, right? So this is just x squared minus x plus 12 over x times x squared plus 6. Okay, so when we do partial fractions, how many fractions will we have? The answer is actually 2. We'll need one for x, and then we'll need another one for x squared plus 6. For those of you who said 3, do you guys want to just share why you thought it was 3? Thought because the denominator was x cubed. Thought the number of fractions was based on the highest exponent in the denominator. I see. Yeah, so it's not based off the highest exponent in the denominator. I guess the best way to think about it would just be to just to write everything in parentheses. So this is the x is in parentheses, and then the x squared plus 6 is in parentheses. So the x will give you one fraction. This part will give you another fraction. The only way you can get more fractions in the decomposition is if any of these parentheses have an exponent outside of it. So for example, if this was x squared plus 6 squared, then that would give you another fraction. But it doesn't have any more power, so it's just 2. Hope that clears it up. So this is an x, which is a linear. So the numerator is just a constant. And then this one is a quadratic, which means the numerator has to be a linear. If it was x squared times x plus 6, there would be 3 fractions. Yeah. So if we want to consider a different example where the denominator was this, Yes, there will be three fractions because technically this is in parentheses. So you need one for x, and then you would need one for x squared. And you need another one for x plus 6. Yeah. All right, so we need to solve for a, b, and c. So if we set our numerators equal, we would have a times x squared plus 6 plus bx plus c times x. Oh, yeah, I forgot to switch windows. You guys should have told me sooner, sorry. There, I was writing on Paint. Okay, so how did you guys solve for a, b, and c here? Let x equal 0. Yep, that sounds good. So if we let x equal 0, we will have 6a, oh, wow, this is equal to our numerator. We'll have 6a plus whatever that is times 0, which is nothing, which is equal to 0 squared minus 0 plus 12. So that's 12. So that means a is 2. Okay. That's one variable solved for. Are there any other convenient values of x we can use? I don't think so, right? So, all right, so let's just choose two other values of x. Let's just choose 1 and 2, I guess. Doesn't really matter. We just need two more equations. So if x is 1, then we'll have 7a is equal to b times 1 plus c times 1. So it's just b plus c is equal to 1 squared minus 1 plus, so that's 12. So when x is 1, we get this equation. And then when x is 2, we will have 10a plus 2b plus c times 2 is equal to 4 minus 2 is 2, that's 14. Okay, so we have these two equations. All right, so now it's just a test of can you solve these two systems of equations. From this equation, we can get 14 plus b plus c is equal to 12 because we found out that a was 2, so I just plugged in what a was. So that means b plus c equals -2. Then from this equation, we get 20 is equal to 20 plus 4b plus 2c equals 14. So 4b plus 2c is negative 6. I'm going to divide both sides by 2, so you get 2b plus c is negative 3. Okay, so we have two very simple equations that hopefully can help us solve for b and c. So using these two, how can we solve for b and c? Any ideas? Because I'm like terrible at algebra here.
You cancel out one variable.
Yeah, how can we do that? I guess we could subtract the two equations, right? So if I was to pair them like this, here's your two equations. And then I subtract them, that would eliminate c, right? Because they both have a positive c in them. So 2b minus b is 1b. And then c minus c is nothing. And then negative 3 minus negative 2 is negative 3 plus 2, which is negative 1. Okay, yeah. So b is negative 1. And then if we plug negative 1 here, then we'll get negative 1 plus c is negative 2. So c is negative 1. Okay. So we found a, b, and c. Great. Let's go back up here. So our original integral is, what was a? A was 2. 2 over x plus negative 1. Well, if it's just negative 1, I'll just write negative x minus 1 over x squared plus 6 dx. All right, so this is where we are now. The 2 over x, we can do that one, right? That one's just ln. What can we do with the second fraction? So this fraction here, how can we deal with that? Any ideas?
Maybe use substitution, but I'm not sure.
There is a better option, actually. So you can split it into two different fractions. I can write negative x over our denominator, and I can write negative 1 over our denominator. So now, just focusing on the 2 over x, that's 2 ln of x. But how can we do this middle fraction? So we're trying to do integral of negative x over x squared plus 6. I'll give you a hint. This one is actually ln if you do a particular u sub.
Would the u be x squared plus 6?
Yes. So u is x squared plus 6. So du is 2x. We just have an x, but that's okay because we can always move constants around. So let's see what this would be. Du over negative 2 is equal to negative x dx. So then we have 1 over u, and then negative x dx is du over negative 2. So now you can see that this middle fraction is actually 1/2 ln of u, and u was x squared plus 6. Okay, so now let's look at the third fraction, and this is where the trig function that I gave you needs to be used. So let me just pull that up. Okay, so usually when we have an arctan integral, this number here is supposed to be 1, right? But how do we deal with it when it's not 1? So you can do like a series of substitutions to get that to be equal to 1. I think I showed that to you with like example 1 or 2 or something. But I find it a little bit too tedious. So if you want, you can just use this formula, which says that the integral is just 1 over a. In this case, a is going to be the square root of 6. So 1 over square root of 6 arctan of x over square root of 6 plus c. Okay. All right. Yeah, that should be the answer. So any questions on that? Okay, how does everyone feel about partial fractions at this point? Yeah, a lot of these can get quite involved. You feel sick. Uh, yeah, no, this is definitely one of the topics that like it's not. I wouldn't say it's hard. It's just very, very long. Like the questions take forever. Yeah. Okay. So going back to our PowerPoints, let me see. So this is the example we just did. Um, this is the last example. And I don't know about you guys, but to be honest, I don't really feel like doing any more examples today. So what I'm gonna do is we're gonna skip this one, and we're gonna call the lesson for partial fractions done. And I will just update this PowerPoint where I'll post a solution for example number 5 into the PowerPoint and I'll re-upload it so you guys see how to do example 5. And we'll just go over how to do partial fractions, in a summary. So let's go over the steps. Number 1, make sure the numerator and denominator are polynomials. So if they're not polynomials, then you cannot do partial fractions. If the degree in the numerator is not less than the degree in the denominator, you have to perform long division first. So regarding that, when I give you a partial fractions question on the exam, it is possible that I can give you one that does require long division. So make sure you show the work for long division if it's required on the exam, okay? Because I know like when you do your homework, you guys are probably just gonna go to Symbol Lab and just get the answer from long division, which is fine, like I don't really care. But you will need to show your work for long division during the test. All right, and then number 3, factor the denominator. That's usually the first step in the easier questions. So you split the integrand into partial fractions, and then how many fractions you have is based off of the table I gave you. And then you solve the system of equations for the constant in the numerators, and then you integrate using ln, or, well, most of the times it's ln, but sometimes you get like arctan stuff. But yeah, that's the whole summary. So on your free time, please complete homework 6.3, and that's it. Okay. So I will see you guys Thursday. Class dismissed.
Have a good night, Professor.
Professor, where can we find our grades to the exam?
I have an Excel sheet, so if you just want to know your grade, just email me and I'll tell you.
All right, cool.